All right, here we go. Let's take a look next session here. I kind of want to take a look at exponential growth here again, and really differentiate the difference here between continuously and almost like compounded. So when we talk exponential growth, last section we were looking at this. We've got this a times b to the x. That is the formula. Everything else is just a variation of this exponential function. But when I use words like continuously, then we got this special one. And before, I think I was calling it this: a equals PRT, like. For money, it's principal and the amount of the balance and all that stuff, but really it's just your starting point and things like that. So let's take a look at this problem. We have two killer bunnies here. Great example here. Fantastic. Maybe we should put some little blood coming out of here. I don't know why they're killer bunnies, but this is the classic exponential growth. Bunnies reproducing here. So if the population grows continuously, I know as soon as you see continuously, you're good to go. Like, it's just write it in there. So when I go ahead and plug this in here, I start with 2 rabbits, so I want to know the amount of rabbits. I can just do something like this. I start with 2. My rate is that percent right there, so it'll be 0.015. And I'm going to do this over time, so that could be t. So I can do whatever time is, I can plug in whatever number you want there. But it's kind of hard to read here. Let me rewrite that. So we've got 0.015. Fantastic. What about if the population doubles every month? So now that's my basic problem. So this is the same. E just takes care of continuous. So my a times b to the x. So I know I start with 2. It's doubling. So there's my rate right there. It's a double. And what happens? This is every month. So I'm going to do something like this. Fantastic. How about the rabbit population every 3 months? So if I'm doing this, I've got my 2 as my starting point. My 2 killer rabbits. They're going to double. If it's just x, that's every month, but that's my time. I want to slow it down. So how do I slow that down? I'm going to say it's x. To slow it down, I'm going to divide it by 3, or it's 1/3 of x. So it's 2 times 2 raised to the 1/3 x, or x divided by 3. So what does that mean for every 7 years? So you start with 2, and it's going to double every 7 years. That's just going to be raised to the x to the 7th power. Fantastic. What if I sped it up? Could you do that? What if the population doubles 3 times a month? Could we speed it up? Sure, if it doubles 3 times a month, it would just be 3x. So the default is just every month, every year, every week. The units don't actually matter. It's just time. Notice I switch back and forth, no problem, as long as your answer will be consistent in that. If you do it in years, you're in years. But you can go back and forth, but it's how often it happens. So that's a cool little thing, though, versus compounded versus continuous. Fantastic. Moving on, let's talk about Half-Life now. I know Half-Life's a great video game. It's pretty awesome. But how does this relate to real life? So in science, you may think of it as asymptotes and some, radioactive decay. So, I was looking at rabbits growing. Now we're looking at decay. So some things lose half of their mass. So they're actually disappearing. So what does that look like? Well, they're shrinking. They decay exponentially. Are they ever really gone? Well, not really. There's always going to be something left. No matter how small, there's going to be something left of this. So here's some asymptote here. I'm not really sure what that is. Gallium, but it's good for tumors. So how do I set this up? Well, it's the same formula. We're really saying it's exponential growth or decay. This is decay. So let me change color. There's a whole lot of red on there. Let's change this color a little bit. So if we start with 100 milligrams of this asymptote, that's my starting point A. How many will be left after? And then we have a couple questions here. So what is my B? Well, it's called half-life for a reason. It's half-life because that's your B. You lose half of it. And what is how often? It'll happen every 46.5 hours it loses half. So how do we do that? Well, you could do something like this. You could say x over 46.5. Now this is not the only way to do it, but it's one way to go about doing it. Alright, so here we go. I moved that down here so we can kind of see the examples here. I love this Half-Life. Great math problem, and it's the game of the year. Woo! Love it. So we'll keep them in here, but a little bit out of the way. Awesome. So let's put these in here. So I'm looking at, this is my equation. This is just one way to do it. I'm going to show you a couple other ways to do it here. But when I have the rate here, I can say 24 hours. Sure, no problem. I want to know what is left. What is the y value left? If I take it, times it by 100, put in 24 over 46.5. Excellent. That's 24 hours. Could I do it in 1 week? Sure, you could do it in 1 week. Just be careful. My constant here, my rate is in hours, so I'd have to say, okay, 1 week, 7 days, 24 hours in a day. We're looking at 168 hours in a week. Is that right? Yes. So you could do the same thing, plug it in, and we're going to say, oh yeah, 128 hours is 1 week, 46 is every half. So you can even estimate it. This answer should roughly be around what? If I look at this, I can tell 128 over 46, it goes in there, what? Just like almost 3 times. So your answer of this, it should lose half of it about 3 times. So let's go ahead and just do that one just to make sure we're cool with typing this into the calculator. What is all this mess? Let's clear this out. Just make sure you're good. But it's crunching numbers. It's 100 times, you can use 0.5, raise it to, and if you have the new operating system, it's nice. You just type it right in. 128 divided by 46.5. Does that work out? 14.8. Does that make sense? So it lost half of it. So it went what? Went from 100 to 50 to 25. So it just went, and then went a little bit more past that. So fantastic. So it'd be 14.83 milligrams. 14.83 milligrams. I think that's what we're in, right? Yeah, milligrams. Awesome. Left over. Fantastic after 1 week. Very good. So what's this for? Well, what's great about this is carbon dating. So I tried to get a funny picture of carbon dating. Denied. Odea turned me down here. I don't know if it thought I was like trying some speed dating or something out there. I was trying to get some. Oh, here it is. Personals. There's Mr. Brust. Always looking, trying to meet people. Yeah, let's get rid of that one. Oh, here, we're going to cover the problem. So what is carbon-14 dating? So maybe you've done this in science, and hopefully you have, because it's super cool. If you think I always think like the dinosaurs, they know how old these dinosaurs are because they find these bones. Every living thing has carbon-14 in it. Everything that's alive has it. So anything that's alive has a certain amount of carbon-14, so we can use it because we know how fast it decays. So we know it decays at it's like 5,730 something years. I don't know, so it's 5,700 something, I think. So I'm going to write that so you can't really tell. That's how often it loses half of it. So you will lose half your carbon in that many years. So a long time from now, half your carbon's going to be gone. So then they can take this. Another way to write it is you can find it as a constant. We can say, oh yeah, this is the rate you're constantly losing. You don't even notice it, but you're losing this much carbon-14 continuously. So that's how they can go back and date things. Let's try an example of this. Let me get rid of this. Alright. Oops. That changed the screen. Change it back. Change it back. Okay. It doesn't want to go. Alright, so let's try one of these. So if I know this, if I decay at this constant rate, this can actually be an E. If I'm continuously doing that, I'm going to start still with my principal or whatever you start with. My constant in this case, so now it's a constant. I can just plug that bad boy right in there. Boom. A little different. It's not a percent. It's the constant which it's decaying. And then now it's just a matter of plug and chug. You have 1,000 liters of this. Or I'm sorry, 1,000 milligrams of carbon-14. Let's say your bus on the way to school today runs over a dog. So you got this dead dog. Boom. He's got 1,000 milligrams of C14 in him. How many will be, if we find the remnants of this dog in 10,000 years, how much will be left? So we can do 1,000. E to the that crazy constant 0.000124, and then what am I going to do? I'm going to type in 10,000 years. This is some of the worst writing I've ever seen. I hope you're not just trying to watch this and be like, what is Mr. Brust doing? This is why you should always listen to the video and have headphones and whatnot. Can't we type that in to make sure we're good on that answer? Yeah, let's do that. Let's plug that bad boy in there. So we have 1,000, and later on we're going to do some more challenging ones as far as solving them algebraically. This is just all about setting them up, making sure they're right. So we've got this constant 0.00012, 4 times, what do we got here? 10,000 years. Did I get that in there right? 10,000 years. Boom, hit enter. And I'm not even going to write that over. I'm going to say there it is. Whoop, there it is. Fantastic. So that's after 10,000 years. Same thing, 50,000 years. So the dog had 1,000 gram. 10,000 years later, he's still got 289 milligrams of carbon. So that's how they can backtrack and say, oh yeah, this dog's 10,000 years old. They can say, we know the rate, so we can actually work backwards, and we'll do some of those later on. So pretty cool on that. Another way would be to set it up as a half-life problem like before. We can say, yeah, I've got 1,000. I know I lose half every. I should have looked this up before I made the video. 5,772. I think it's that 5,732. And then I could go ahead and plug in my time here, and I would be good to go. So I lose it that often. I'm sorry. I don't. Did I not say that right? The T doesn't go there. Where does the T go? Just making sure I lose it every one of those. I'm going to lose half of it. Fantastic. Very good. Moving on, what's some other cool stuff you can do with these with E? Just an amazing number here. A lot of learning curves, population models, things like that. Here's a crazy function right here. So this is just crazy function. Twinkie almost went out of business. Hostess was going out of business. I can't believe it. The icon, unbelievable. I think they're making a comeback. They're going to make a go of it. Thank goodness. So let's say at a Twinkie factory, they know from their past experience that employees can inspect this many Twinkies modeled by how long they've worked there. So apparently, let's see what's going on here. So T is the number of Twinkies inspected per hour in hundreds, and T is the time in days. So here is just a nice thing. Can you graph this and tell me what's going on here? So you may want to pause it, try to graph it, try to get your friendly window. Here we go. If you did it, does it look like this? I already preloaded mine. So in my y equals, I have it. This is what it should look like in there. You know, if you zoom standard, you're not going to get a very good window. I think, is this the zoom standard version of it? Not very good. So let's go back and think about this mean. X stands for, in this case, T, time. So time is what? Time, it's not Twinkie. It's weird. We got T of T, capital T, lower t, time and Twinkie. Maybe we should change that a little bit. This is in days. So how many days? Let's look at a week here, maybe. That's 1 week. And then the Y is how many Twinkies they're looking at. So the lowest would be 0. This is how many can they inspect. Gosh, I don't know how many Twinkies you can expect. It's in hundreds. I'm going to guess 60 because it's in hundreds, so 60 hundreds. I could be way off here. Counting by 5. Let's graph it and see what happens. Oh, not too shabby. Excellent. So we've got something like this. And maybe we want to see more. Maybe we really want to see 2 weeks, so we can type in 14 days. So depending on how long you've worked there. So T is the number of Twinkies expected per hour, and that's the time in days. So what does this mean? Let's just trace a point. Boom. What does this actually mean here? Let's talk about this. If I plot a point on here, this says 722.73, so this just means on day 7. So on the day 7, you can actually inspect 22.7300 of these. So what's happening here? Can you tell me what's going on? As you have worked at Twinkie longer, what is happening? You are inspecting more Twinkies. Does it ever level out? Like, what if you've been there for like years, man? What if you've been there 1 year? What happens to the graph? Check that out. So at some point, there's only so many Twinkies you can inspect, no matter what your experience. So you hit this line right here. We're going to talk about finding that. So pretty cool way to see. You know, after I've worked here long enough, I'll be a master Twinkie inspector. Woo! Great job, I imagine. If you like Twinkies. And in the finale, here it is. This is really what this section's about. It's the last slide. It's the logistics model here. So this is a great, cool model. It looks something like this. Let's just do it, and then we'll define it. So we're looking for things with E. Can we put this in the calculator? You may want to pause and try to put it in there. I'm preloaded here, so let's turn this one off, and I'm going to go down to my second one. Just be careful. When you're typing this into the calculator, make sure that you got parentheses. You don't really need them for the top because there's only one thing, but when there's more than one thing, make sure you use parentheses on top, parentheses on bottom. So I preloaded mine, so I'm good to go. So if I go to graph this one, you know, if I go to that standard window, it's probably not very good. So we got to kind of tweak it so I can see it. I can't see anything on that one. So this is kind of crazy. I was hoping I'd get a little something. Did I not turn it on? You can't see it if it's not turned on. Yeah. I was hoping to have a starting point. Yeah, definitely make sure that's highlighted so it's graphing. There we go. I got something going on here. So logistics models are different. They're kind of like what we were looking at before, but they've got a really cool shape to them. And the shape looks like this. They're going to come along here, go up, and come along like this. Or you can have logistic model in a decay mode where it does this. So it turns out things in real life do this, you know. Learning curves, that looked like part of it, but different things throughout will grow until they can't grow anymore, and you actually get these asymptotes like this. Is that cool? So you get 2 horizontal asymptotes, one from each side. So pretty neat. So when I go back to this graph, I looks like there's one at 0. I need a little more, what do we got here? A little more y max. Maybe we need to go to, I don't know, 30? Counting by tens. Let's see what that does. And so I've got something like this. Whoa! I got to go more than 30, huh? That thing's taking off there. Let's try this. 300. I think that's going to be too far. It's not even far enough. Woo! Keep this bad boy going. Oh, right. So we're going to go up to 3,000. And I'm going to start counting by hundreds down here. So let's kind of get some checking. We'll get some tips in here on how to get better at what's going on here. But there it is. See how it comes up. So I went a little bit too far here. In fact, maybe you notice where I should have gone. Let's tone this back down just so we can see a little bit better. I'm going to add a little more X so we can make sure we see it. Let's go to 20. And I'm going to turn this back down to 2,000. 1, 2, 3. Alright, so now we got this picture. Boom, there it is. So it looks like it's coming in, and so that's definitely a logistics model. It's coming here. It never touches 0, so don't say it touches 0, comes up, and then it goes like this forever. So you actually have asymptotes here. 0 is an asymptote, and this. So what is going on here? What is the limit as x approaches infinity? So we're talking, what is a horizontal asymptote? What is that number it's maxing out on? Maybe you know it. Maybe you can recognize it. If you don't, go to your table. You know what happens is x is super huge. You know, when x is 100, what number is it approaching? When x is 1,000, what number is it approaching? And we can already tell when x is a billion, million, what number? 1,600. Excellent. Yeah, it's just approaching the top of the fraction. So when I do this, the limit is 1,600. That's the highest it'll ever get. This is 1,600. Fantastic. What about negative infinity? So there's a little negative sign in there. So as it approaches negative infinity, where is this one? In this case, it's 0. So the y value is approaching 0. What's the y-intercept? Maybe you can tell. You know, that's when x is 0. What's y? What? Oh, I did that backwards. Sorry about that. Let's just delete that. So if x is 0, what's y? So if x is 0, what is the y value? We'll plug 0 in here. What's going to happen? What is e to the 0 power? What's anything to the 0 power? It's 1. So what do you really have on bottom? You have 1,600 on top, 1 plus 799. So you've got 800, and so what is this? This should just be 2, shouldn't it? Let's double check, make sure we're good. When x is 0, what is y? Boom, it's 2, so we're good to go. And then domain and range. So if I'm looking at this function right here, the domain, all real numbers. Everything goes in there, so you're good on that, all real numbers. Do we have a limit on the y? Sure, we definitely do. We're really saying, you know, the y value is greater than or equal to 0, but it's less than, equal to, what am I doing? I feel like I'm making a ton of mistakes, I apologize. It's greater than 0, but it's less than 1,600. So if we're using notation for that, we're saying it can be from 0 to 1,600 is the range. Fantastic. So really, logistic models can take a couple different forms. You know, this is the form we're looking at right here. There's that a times b to the x. So it is an exponential function wedged in there with a constant on top, and it's that 1 plus it. Don't freak out if you see it written like this. This is a great way to do it, or something like this. When we put e in there as a constant, that's still 1 plus a times b to the x. The b is just this e to the negative k. So you're good to go there. All right, I hope that helps, and good luck on the mastery check. Peace out.